to welcome you to another Biostatistics lecture series. Our speaker today is Wang, and our lecture series is sponsored by the CTSI and the Department of Biostatistics. If you haven't already, please pick up a evaluation, and you'll see on the back there's a speaker disclosure. And if you could fill out our evaluations, that would be most appreciative. If you don't have one, please raise your hand. I'll bring it to you. And there are handouts as well, except for we're missing one slide that he added at the last minute. But they will be on our website as well, so you can also get that there. The evaluation is important, especially if you want a CME credit. Also, if you could register in the back, if you haven't already, you could do that when you leave. There's some registration forms as well. And I just want to welcome Tao. You can raise your hand.
All right. Thank you everyone for coming. And first, I think I would like to clarify. I'm currently an assistant professor in Division of Biostatistics. There's a typo on the flyer. So today, I would like to talk about the logistic regression. Okay, it's another type of regression, followed by I think a linear regression given last month by Dr. Meijie Zhang. So there's some speaker disclosure. I do not have any relationship to or financial conflicts to disclose here. So this is the outline of my talk here. I will start from two simple examples and let you see what kind of situation we are facing, and then why we need to use logistic regression. And then I will talk about logistic regression and what the logistic model is, and how to actually fit the model, and then what the logistic regression can do for us. Okay, so I will focus on kind of two common purposes we usually face in medical research. One is for association tests, another for the prediction and the classification of patients. And then give you a brief summary. Please stop me at any time if you have questions. Okay, so the first example I would like to talk about is a case control study. It's quite popularly used in the medical research, basically quite efficient in recruiting patients. This is the kind of data collected quite a long time ago about the lung cancer and the smoking. So you get the case group and you get the control group, and then you have smokers and non-smokers. So just classify the patients, and also by the smoker status, you get a kind of 2x2 table here. It's usually called the 2x2 contingency table. And then you have 688 smokers. They also get the lung cancer, and then 650 they didn't get the lung cancer. And then for the non-smokers, they have 21 cases and 50 non-controls. And then usually for this kind of table, what we usually do is to calculate the odds ratio. So in order to get the odds ratio, we usually first calculate the odds. Okay, odds of being a case in smoker group, that's easy to do. Just the number of patients divided by the number of controls in the normal in the smoker group, you get 1.06. And then odds of being a case in non-smoker group, you calculate in a similar way. You get 21 divided by 59, you get 0.36. And then the odds ratio of being a case, okay, in smokers group versus non-smoker group, just the ratio of the two odds. Okay, that's we usually call that odds ratio. So it's about 3. What it means is, okay, in the smoker group, okay, the odds of getting the case is about 3 times the odds of getting the case in a non-smoking group. Okay, or you can see the 2 times larger okay, the smoking group than the non-smoking group. And then you can also do an association test. Okay, the association test basically say, okay, if there's no association with the lung cancer with the smoking status, you would expect the 2 odds are the same, all right? And then equivalent, the odds ratio is 1, okay, because the odds ratio, the ratio of the 2 odds. And then statistically, you can construct the null hypothesis. It's basically O are the odds ratio equal 1, okay, and the alternative with the odds ratio is not the 1. And then the typical test statistic you can use is the chi-square test statistic. Okay, it's just observed minus expected, take square, and then divide by the expected number of the patient. And then usually this is a 2x2 continuous table. It follows the chi-square distribution with degree free freedom 1. Okay, so you can easily calculate this x square and do a kind of association test to get the p-value also. And then another thing we can do is we can also construct the confidence intervals for the odds ratio. Okay, that's we also typically do. For the 95%, that's kind of usually the kind of level we use, and then we get the confidence intervals for the previous kind of odds ratio estimates. We get 1.79 to 4.95. And since this confidence interval it doesn't contain 1, okay, so at 5% significance level, we can reject the null hypothesis. And our conclusion is smokers have higher odds getting lung cancer than the non-smokers, all right? So this is the 5% basically corresponding to the 95% confidence interval level there. So that's basically controlled false positive rate. What it means, this confidence interval, use this confidence interval or reject your conclusion for rejecting this null hypothesis. Basically, you make the false positive, the chance is less than 5%. You get a very controlled false positive rate. So this is a simple question, and then we may ask more questions. Probably our research problem is more complicated. So one question you may ask is how to adjust for other risk factors, all right? The gender or age, okay, could affect the odds of getting lung cancer. And then if you have those other risk factors, how to kind of build a model there, okay, to include those risk factors. So a model including more risk factors certainly will give you better predictive power there. So to answer this kind of question, we need to kind of go one step further. Basically, logistic regression can help you do that. The second example, I would like to talk about the coronary heart disease. Okay, this is the leading cause of death in American women, and the risk factors for this one. We already know, okay, age, smoking status, high blood pressure, high cholesterol level, and obesity, and a number of other, another variables may affect this, associated with this disease. And then we take a look at the age specifically. Okay, the age and this is the disease, the coronary heart disease. Okay, suppose this is a part of the data got from a bigger study there. I just listed about 33 patients here. The subject here get involved in this study, and this is the age. Okay, from 22 go to 30, go to 40, and go to 81. And the disease status. Okay. 0 means this subject didn't get the disease, and the 1 means this is the patient there. So 0 basically kind of normal people, and then the 1 is the subject. Okay, so why we need to look at the age? Okay, age is the risk factor, but compared to the previous case control study, there's a difference here. What you can see, the specialty is age is a continuous variable. Okay, so in other words, how to construct the kind of a contingency table? You cannot get a 2x2 contingency table, because age is continuous. Okay, if you think at each age level, you can think of some people get disease, some people didn't get disease, and then basically you have many levels of age, and then how to kind of assess the association between age and the disease in this case. So one thing you can think, okay, because age continues, we probably just think of the means of the age, okay, in two groups. We have patients, we have normals, so we just keep it to the normals, see, with the average age 38.6 years old, and the diseased one probably 59 years old. If you do a simple t-test, you can see the p-value is very small, and then probably you can see, okay, the ages are different in the normals and the cases. But the problem is, okay, this kind of assessment is not so informative. What it means is it doesn't give you the magnitude of the association, all right? And also depending on study design, this kind of comparison may not be so meaningful there. So what we would like to see is to kind of build a relationship between the age and the presence of the CHD, okay, the disease, and how to do that one. So in order to build a relationship, I think usually we would like to get a kind of so-called graph to see what happens there. Okay, so if we make a dot plot, all right, so the x-axis gives the age of years, and the y-axis gives yes, no, all right, so you plot in this way. But the situation you can see is, okay, because the disease is classified in yes and no, just the binary outcome. So you can see the dot plots, just the kind of cluster at the 0 and then the 1, 0, and the age is continuous. But then if you think, okay, how to fit kind of build a relationship, can I just fit a linear model here? So that's the linear regression you learned last month. So if I just simply fit a linear regression curve here, or straight line here, it doesn't help much, okay, because this fitted line from this one, what it can help us to identify. Basically, it's kind of give you the similar situation like compared the two means before, and couldn't get you more information there. So when this outcome variables, basically it's so binary, like the presence or absence of a disease, okay, it makes more sense to consider the probability of having this disease at the different age levels there, all right? So what it means is we probably can categorize the age into multiple groups, okay, and then look at the presence or absence of a disease in each age group. So if we kind of categorize age by decade, okay, we can get this kind of intervals there, and then this is the number of people within each age group, and then this disease, how many how many persons get disease in each age group. Okay, in the first age group you have totally 9 people, but 9 of them get disease. Okay, and then the second you have 6 people, but 1 got the disease. So and then you can compute the proportion of how many 1 divided by 6, about 70% get the disease. So you get this kind of proportion of the patients. And if you plot them, just get a graph, and you can get this kind of curve. And this kind of curve gives us kind of more interesting thing to think of. Okay, we have age groups, and then we have the disease, but now the age, instead of just take a 0 and 1, we have the proportions, okay, between 0 and 1. And if we look at the curve pattern here, it looks like, okay, logistic curve. Okay, statically, logistic function gives described by this form. Okay, this is a logistic curve. You have 2 parameters in this case, and then if x, think of x at age, and y is just the presence or absence of the disease for its probability, and this is the logical curve we have here. So what's a logical model we can build for this case? In this case, basically, if you define y just 0, 1, it's still binary. Okay, it's you get 1, you get the current disease. If 0, if it's not the patient there. And then think of the not just y equal 1, but think of the probability of y equal 1. Okay, that's basically the proportion of patients, and then within each age group. So if I express it in this way, this is basically logistical function. I just direct plug in, and there are 2 parameters, alpha and beta. Okay, this and then divided by this 1 plus that 1. And then this exponential function is always kind of positive. And why we need to use this denominator, 1 plus this 1 makes this probability always go from 0 and 1. Okay, so it's very controlled. Always positive and always between 0 and 1. And then we have good method to estimate this alpha and beta. We will talk about that later. So just do a little bit of algebra and think and let us see what really means for the regression coefficients here. Okay, this is still the previous notation. I just use, okay, just write this part as pi, okay, make it simpler. And certainly it depends on age. Given different age, I have different probability there. And then this is just the logical function I have before. Do a little bit of algebra, you can see, okay, this pi h divided by 1 minus pi h will become exponential of alpha plus beta times h. Okay, you just do a simple algebra. And if I take the log transform on both sides, you will get log of this 1 equals alpha plus beta h. And then you can see the right side becomes a linear function for h, all right? And what the right side means is pi h 1 minus h. Okay, pi is the probability of get the disease. So this is the probability to get affected for the on the denominator. And the denominator 1 minus this 1 is actually the not affected. Okay, the probability of not affected. So basically, given the age group, this is the pi. Basically, this gives you the affected probability divided by the non-affected probability, and what it is back to the previous odds ratio. Okay, it's the odds, basically odds of getting affected at age, the specific age. So this quantity basically is the odds of this one, and then if we take the log odds, basically becomes a linear function for age. So we just get a little bit continue. So this log odds age equals this kind of linear function. Okay, and then if we think of let age increase 1 unit, or you can think of, I just think of another age group. Okay, and then I have age age plus 1 equals alpha plus beta times age plus 1. Okay, and then you can see the first equation and the second equation. If we just take the difference of the first equation from the second equation, what we get is beta equals is log this part, log odds minus log odds, and then the log transformation has the nice property, right? Difference becomes kind of ratio, and then you can see, okay, this is the odds age plus 1 versus odds age. So this part is odds ratio, okay, between age plus 1 group and then age group. So if I take the exponential beta, what it means, exponential beta will be exactly the same as this odds ratio here. So what it tells you is the E beta, okay, as long as we get estimates of beta, the E beta is the odds ratio of having the disease for age, for X equals age plus 1 group versus X equal age group. Okay, there's a typo here, sorry about that. And then basically the 1 unit increase of age, this is the odds ratio measure. Okay, so if you fit a logic regression, gets that beta estimates and takes exponential for that beta, basically that's the odds ratio estimates for the age variable there. Okay, that's a nice thing here. And then it is just to kind of summarize the previous logical model here. You have kind of this right side is pi 1 minus pi, that gives the odds. Okay, so it's odds of having this disease at a certain age. And then if you take the log transform, you get this linear function, and then basically this kind of complicated function, but remember this just the odds of that one. So this is log odds, and we call that some logic transformation of this one. And then the E beta is the odds ratio of having this one for H plus one group versus H, and then beta is the log odds, all right? And then a little bit more complicated thing about how to interpret this intercept, okay? And alpha there. Alpha usually we are not so interested in interpretation that one. It's complicated sometimes, okay? For the prospective study, alpha basically gives you the estimates log odds. Alpha gives you the log odds of these at H0, okay? And then but H equals 0, it doesn't mean anything there. But this one basically is directly linked to the prevalence of disease in your sample population there. But if you are talking about the case control study, it's more complicated, this alpha, because how the sample rate of the cases it's basically also getting involved. Alpha will depend on the sampling rate of your cases, okay? And so it's complicated function. But anyway, I think we are usually in retrospective study we are more interested in the beta, the regression coefficient instead of the intercepts, intersections. So we made some assumptions in order to make that model there. So usually for the logistic regression, we need to assume independent observations. Okay, basically you get the sample, and each subject in your sample is unrelated to the others. And then another assumption we made is a linear relationship between log odds of having this disease and the covert age, right? So we assume, okay, the E beta is the odds ratio of age plus 1 and then versus the age group, but for any kind of value of age. Okay, for age 20, you have the E beta that gives you the odds ratio, and for age equal 30, you still have the same thing. Okay, that's kind of assumption we made. So what it means is you have constant odds ratio across all age values. Okay, and this may not be the case, right? So for this specific study, actually, there's evidence that the odds ratio of this one may change over time. So, in the table, I only list the 33 subjects. Actually, it's a quite large data set. And if we break the age into intervals and calculate the odds ratio, we can see, okay, the 30 to 39 versus 20 to 28, and then this two groups, the odds ratio is 1.74. And if you think 40s versus 30s, odds ratio increases to 3. And if you think 50s versus 40s, the odds ratio increases to 4.46. What it means tells you the odds ratio increase over time, over age. Okay, it's not just keep constant if you compare the consecutive groups there. So one method we can use in statistics, because in this case, we can categorize the age into multiple groups. And then for each of the age intervals, okay, certainly when you do if you want to do this, you need each age interval should have a reasonable number of observations. But as long as you have enough n number there, you do in this way, it allows you our logistic regression model allows you to estimate the odds ratio, based on different groups. So, in other words, the assumptions we made before is not a kind of the necessary assumption. We can certainly lose that assumption, depends on the requirement you need to make there. So each of the age intervals should have a reasonable number of observations, and what's the step for doing this one? You categorize a continuous variable into multiple groups, kind of like the step function to approximate a nonlinear curve there. So if we continue the previous example, okay, we have this kind of log odds equals a linear function, but in this case, we want to break age into several groups. Okay, suppose here we break, by just break the age into 3 groups. Okay, so age less than 30 is a group, 30 to 60 is a group, and bigger than 60 is a group. So we have 3 groups. And then if we introduce just age 1 equal 1 for patient, if the patient gets 30 to 60 and 0 otherwise, and so this variable, if it's bigger than 60, we define as 1. And then for the 3 groups, when you do the comparison, okay, we basically use 2 variables fit in the model, and then you get the E beta estimates for j equal 1, 2. What that means gives you the odds ratio of group 1, 2 versus another baseline group that's the less than 30, that's the youngest group. Okay, so you break 3 groups, but when you fit the model, okay, you want to know, okay, the second group was the first and the third group was the first. And then you fit the model, you can get this estimate. But how about the second group and the third group? You can basically also estimate the third group, odds ratio between the third group and the second group just from the model. Okay, but this is a direct estimate to get the odds ratio between the groups 2, 3 versus first. But the 2 and 3, between the 2 and 3, you can also get that odds ratio estimates. And then certainly one question you may ask, okay, why you pick up 30 and 60? Is that reasonable or not? Okay, that's how to select the cutting point there. So the number of intervals and the cutting points of the intervals should be predetermined based on clinical information knowledge. Okay, that's quite important when you do this kind of data analysis. Sometimes as people think, okay, you can let the model do it. Okay, please select the cutting points based on the statistical models. We can do that one statistically. Okay, there's a optical model selection procedure to select the cutting point based on the maximum likelihood. But remember that when this kind of method tends to find a significance more than it should be. All right, so this may lead you to the inflated false positive rate. Okay, usually we control the false positive rate by 5%, but if you want to do in this way, your estimates, you may likely to report the association, but the error of chance may be inflated. Okay, that's just one thing keep in mind. So we usually do not recommend to do in this way. So for this coronary disease, okay, certainly there are a number of other risk factors. We have the gender, we have age, smoking, and other risk factors. And then how to build a model, can allow you to include multiple risk factors together, okay, instead of just evaluate one at a time. So in order to do it, okay, the logistic regression can easily be, the logistic model we talked before can easily be extended to multiple logistic models there. Okay, you still have that Y defined, but just 1 if it's get disease, if 0 is healthy, all right? And then you have K, risk factors, basically K is the number of risk factors you have. Okay, age, gender, smoking status, that gives you 3, and if you want to add more, you just increase. And then this pi is still similar, right? Only changes this kind of probability. And how about the model? This is still log odds, all right? But the right side, you just, previously you have beta 1 age, but now because I have more risk factors, I just increase the number of parameters I want to fit in the model there, okay? So all the betas, 1 to beta k, we usually call that regression coefficients, just like the linear regression model. And then beta 0 is the interaction term, all right? So the extension to multiple risk factors is straightforward as long as you get the logistic model worked out there. So the logistic regression between this one and a set of predictors, and then the linear relationship between this one and the set of predictor variable. But like I said before, in the example, this linear relationship seems strong, but it's not as strong as the linear regression model assumptions we have here, basically because we can break the continuous ones. If the age seems it doesn't have the linear relationship, we can categorize it. okay, make it into multiple groups. Okay, so this log out basically is a linear function of your risk factors, and then you can see the odds is the exponential function of your risk factors. So the model itself just the kind of based on the exponential function. And we talked about the interaction, the interpretation of model parameters. But in the multiple logistic regression model case, a little bit more complicated than the previous one. So think of, okay, here I have a variable. Suppose we consider the gender as a risk factor here. Okay, we have male and female. If male 1 and female 0. And then if for males, just based on the model, okay, the odds of this one is the exponential of this function. For females, okay, for females I have the x1 equals 0, so I just plug in x1 equals 0, so I get beta 1 times 0. That gives me 0. And then for males I have odds, for females I have odds. So the odds ratio of getting affected for males versus females, okay, basically I use the first equation divided by the second equation. I get the left side gives you the odds ratio between male and female. The right side, okay, beta 0 exponential get cancelled, beta 1 gets left, and all the others, beta k, xk get cancelled. All right. So what you left is the exponential of beta 1. So and then how to interpret this one? This basically the odds ratio of getting affected between male and female, but just add one piece of sentence here, while assuming the other cohorts are the same. So if you want to compare male and female, suppose all the other risk factors are the same, and then E beta basically the odds ratio, right? So how to interpret this one? I think in words, basically, for example, if you have the E beta 1 equals 0.33, basically it means the getting affected in males, all right, is about 33% of the odds in the females, all right. Or in other words, you can see there's a 6-7% decrease in odds compared to the females. Okay, that's basically the language you can use if you get these estimates there. So it's the E beta basically can be interpreted as a percent increase or decrease in odds ratio compared to the reference group, basically the female in this case. So for the gender, it's probably easier because it's a kind of a binary variable. It only takes 0 and 1. So how about the age? Okay, age is a continuous variable, like we talked before. Okay, in that case, the E beta 1 is the odds of affected. Okay, and then we talked about you increase 1 unit increase. Okay, and versus the age itself. Then the E beta 1, in this case, is the odds ratio between x plus 1 group versus x1 group. Okay, that's the same as as the age situation we talked before, and then still need this piece of language here while assuming the other cohorts are the same. Okay, and certainly it's implicitly assume a constant odds ratio across all values of x1. Okay, if it's not the case, we categorize x1. All right. But this one basically gives you the interpretation, basically how to interpret that. So what the multiple logistic regression means? Okay, basically it's a regression method. Okay, it deals with the case when the dependent variables or the outcome variables is binary. Most of the case, we focus on the disease, either get disease present or absent of the disease. It's always get a binary outcomes. We usually apply logistic regression. Okay, that's a major difference from a linear regression model. In the linear regression model, you have continuous measured outcome. And then this model also allow you to kind of consider the many predictive variables or risk factors. Okay, that's the same situation like the linear regression model. And then these predictive variables can be continuous like age. Okay, or can be nominals like the gender. Okay, or can be categorical ones. Okay, if I break the age into different groups, I get the categorical variables. And the regression coefficients of this logistic regression model are often being interpreted as odds ratio, right? So the linear regression model, we talk about continuous variables. Logistic regression, we talk about binary outcomes. And then another difference we can see, the linear regression, we usually examine the variation of the outcome variables explained by the predictors. Okay, that's the R squared. You talk about 80% of variation in your outcome can be explained by a set of risk factors. Okay, that's the language you use in the linear regression. But in logistic regression, okay, we model the probability of basically log odds. Okay, log odds of your event. So we are talking about the probability of the event. What's their relationship with the predictors? So the odds ratio is the effect of the predictors on this kind of a log odds. Okay, that's another difference you can see compared to the linear regression model. So we are not talking about the changes in the outcome itself. Okay. So we get the logistic regression model and how to fit the model. Okay, this part is a little bit more complicated. Okay, in the linear regression model, we can get a closed form solution. It's well known like the least square estimates. Okay, but in the logistic regression model, because exponential or logistic function is nonlinear, so we need some numerical approach to do it. But nowadays, it's a traducing with a computer and a software package. Anyway, I think there's one of the methods is often used to fit the logistic regression model is a so-called the maximum likelihood estimates. Okay, you probably can see this kind of terms quite often, but just one way to estimate the regression coefficients. And the likelihood basically is a function to reflect how likely your observed data is given the logistic model, right? And then the MLE, the maximum likelihood estimation, basically the way to maximize the likelihood function and get the estimates. Okay, and this model fitting can be done by many softwares. I think I just list the SAS, that's and the SPSS, and the R language is a free package, and there are some other packages like Stata and Minitab. Some of you may know one or two of them. This kind of package there. Basically, it's easily done to fit the model there. That's not a big issue. And then what can the logistic regression do? Okay, that's probably our interest there. We can fit the model, get to the logistic regression, but what it can do for us. So first thing I think it's probably most common thing we would like to see is to test for the association of a predictor variables with adjustment for other confounding factors. Okay, we probably ask. Okay, for example, for the first example, okay, the lung cancer, we talk about the smoking effects. Okay, we can estimate the odds ratio, but at that time we didn't adjust, a gender effects or other factors. But with the logistic regression, multiple logistic regression model, we can get estimates for the adjusted odds ratio for the smoking status. Right, that's one thing you can do. Basically, adjust by age, by gender, and other risk factors. And another thing it can do is why we need the multivariate analysis. That's kind of another question you may ask. Okay, the multivariate analysis with the adjustment basically gives you more reliable estimates, and your conclusion will be also more reliable. Okay, fit the multivariate model, you get the p-value. That p-value is more reliable than the p-value you get without adjustment for the other risk factors. Okay, so this is the why we need to use the multivariate analysis, just like the linear regression. Okay, why we need multiple linear regression model instead of just one univariate analysis. That's the same situation. You want to piece out the effects that's purely contributed by your risk factor instead of others. Get rid of the confounding effects. Okay, so the association test, how to do it? Okay, in logistic regression model, basically you fit the regression model. Okay, you get the estimate beta, and the software package not only can provide the estimate for the beta, it also can give you the statistical test. Okay, similar to the chi-square test we discussed before, the kind of contingency table, the chi-square standard Pearson chi-square study, but this is more complicated. But it's kind of a similar situation and just kind of an extension of the classical chi-square test. And then it depends on how many factors you want to test. Okay, it can give you the p-values. What it means is you can test the one factor at a time. Okay, suppose age. Okay, what's the effect of age? You get the p-value. But if I break age into two groups, you can test simultaneously. Okay, the two age odds ratio should be zero or not. Odds ratio should be 1 or not. Okay, you can test the overall effects of age even though you break the age into multiple groups. And then you can also test simultaneously. So if I think age and gender both are risk factors, okay, I want to test if they both contribute something there. You can test simultaneously several risk factors together, okay? And most often you get always the chi-square, and the k is the number of risk factors you want to test. So what can the logistic regression do? Arrow basically you can rank the relative importance of the risk factors, okay? Because you are now considering all the risk factors together. And then when you fit the model, you get the p-value for each factor, risk factor. And then you can see, okay, what's the relative importance of risk factors. And another thing, probably sometimes we are also interested in to assess the possible interactions. Okay, that's kind of a hot term. People always want to see if there's a kind of gender by smoking interaction. Okay, those kind of interaction things. Basically, the model can also allow you to do that. And then another thing is after you build the logistic regression model, it can allow you to predict the outcome variables, okay, based on your risk factors. What it means is you build the model based on your observed data. But now if one new patient come and then ask questions, okay, I have this kind of disease, what's the chance? Okay, one patient, if it's probably this patient is not well identified, okay, wants to know, okay, what chance really gets that disease, okay, and then he or she presents the risk factors like age, 35, okay, is the male, and then what's chance of get that disease. Okay, so this model basically allow you to do a prediction on that, and then classify the patients, right? Basically, for a group of people, their disease status are not so surely known, and then you can give the classification. You can see, okay, with such kind of probability, this person probably should be classified as a disease group, okay, or likely to get with 80% chance to get disease in the future. We'll talk a little bit about interactions. So what interactions means, we always talk about the interactions. So this just show you an example what the interaction means in the logistic regression model framework. So here we have the X1, suppose that's the gender risk factor, male and female, like just defined 0, 1, as we defined before. And then this log out equals to this age and then the gender, okay? Without this interaction, we just use beta 1 times age plus beta 2 times X1 times gender. But you can add the age times the gender gives another term, is basically tells you the interaction. So what it means, basically if you just think of this model, I have man, X1 equal 1. So based on this model, the left side, the log out equals alpha plus beta 2, okay? Because x1 equal 1 and x1 equal 1, so I have beta 3. So for the age, previously it's beta 1, now I get beta 1 plus beta 3 age, all right? For women, this x1 equals 0, so this interaction term cancels out, is 0, so I still have the alpha plus beta 1 age, So what it means, you can see for the man, I have log outs in this case, in this way, and the woman given by this formula. So now, what you can see is, okay, for the woman in the age group, okay, the E beta 1 still the odds, okay, for the woman, but then in the man, the odds for the age becomes beta 1 E, it becomes E beta 1 plus beta 3. So the age effects differ between man and woman. Okay, so if you do not want to include the interaction, what it means is for male, whether it's a male or female, the odds ratio of age is always the same. Okay, include the interaction, it will tell you, okay, if there's a strong interaction there, it tells you the odds will be different, between man and woman. Okay, that's basically what the interaction means in this case. Okay, so in woman, 1 unit increase of age has the odds ratio like E beta 1, and in man, the odds ratio will become E beta 1 plus beta 3. Okay, beta 3, when you have a strong, significant interaction, beta 3 will not be 0. Right? So that's the difference. If you think this is a reasonable question, that's basically what the interaction you want to fit in your model there. Right? To do another purpose of fitting the regression model is to do the prediction and classification. I mentioned that before. And then, so from the fitted model, a predicted event probability basically already given by the model itself. So it's very straightforward. As long as you have the model, you can compute this probability given the risk factors, right? And then you can classify the observations. And the classification of the observation is a little bit tricky there. Basically, okay, for each patient, for each person, I can give the probability of that this person get the disease. And then how do I classify them? It depends on the threshold, right? Suppose I have 60%. If it's above 60%, I classify, okay, this person likely get disease. I classify as a disease group. And below 60%, I classify as a non-disease group. So there's a cutting point you need to pick. So how to pick the cutting point, we will see, get some help for that one. So and then if you want to see, okay, how can I select the cutting points? Okay, we need to think about a little bit some terminologies there. Okay, so the predictive success of the logistic regression model can be assessed by looking at the classification table, okay, basically showing the correct and the incorrect classification of the patients. That gives back to two, I think, probably familiar terminology in the medical kind of research. One is called sensitivity, another is called specificity, right? So what that two terms means? The sensitivity basically is a proportion of events, response that were predicted to be events. What it means is the sensitivity is suppose that patient, person really is a patient, okay, and then your prediction make the right prediction. You classify him or her to the patient group, okay. What's the chance of you get that correct on diagnosis? That's basically the sensitivity. Actually, statistically, that's equivalent to the power, right? And another specificity is the correct way to for the non-events. So this person is didn't get the disease, and your prediction is also right. Okay, this person is classified in the control group, non-disease group. So what's the chance of you make that correct diagnosis? That's the specificity. Statistically, that's basically 1 minus false positive rate, okay? Or the type 1, type 2 errors. For each diagnosis, we always have type 1 error rates, that's basically false positive rate, and type 2 error rates, that's false negative rate, right? So this kind of two terminologies basically describe the same thing there, but just use the 1 minus for the specific part. So for each cutting point, okay, we can calculate that specificity and the sensitivity. Okay, suppose you get the model, you usually get a new group of people, and then do the classification, and then you at each cutting point you get that sensitivity and the specificity. So for each cutting point, I can get 1 point here. If I get the whole curve plot here, it tells you something about how to pick up the cutting point. Okay, so what it means is okay. For the better ones, I would like the sensitivity, the higher the better, right? For the specificity, I also would like the specificity, the higher, the greater, the better, right? And then if here I use the axis is plotted by the 1 minus specificity, so the smaller the better, okay? So what it means for the x-axis, I would like to pick up the near 0, and for the y-axis, I would like to increase to 1. So what it means is this part of the curve probably the best, best place to pick up the cutting points. Okay, basically it gives me higher sensitivity and lower higher specificity. All right, so this part curve probably I would like to pick up 1 point like this, showed here. Okay, so the cutting point, you always have a trade-off there. Okay, so if if you do not want to pick up this one, pick up kind of a little bit upper right, and then this one gives me higher sensitivity, but on the other hand gives me lower specificity. All right, so that's most often you always can see a trade-off here, but that's the way it is. I think that's the real world here. So this plot usually we call that ROC plot. Okay, this plot allows you to evaluate how good the predictive model is. All right, and then if you have kind of multiple models there, okay, when you build the regression model, it's usually you do not end up with just a single model. Okay, it's the best. Sometimes you have 1 or 2 models. For example, you do the model selection and then put a set of risk variables in. But sometimes, okay, probably think of the gender variable. It may be put in the model. It may not be put in the model. So, and then you ask the question, should I put that in the model or not? Okay, certainly there's statistically there are some help you can get based on the p-values. But sometimes, clinically, you think it makes more sense to put the gender in, even though it statistically may not be significant. Okay, if that's the case, and then you think, okay, I probably can evaluate the 2 different models use ROC curve. So how to do this one? Basically, you plot the curve for each model, and then there's another parameter here. You see, this one basically take the area under this ROC curve. Okay, so the area the bigger, okay, you get better predictive power there. So the diagnostic performance of a logistic regression model can be quantified by computing this kind of area under this ROC curve. Okay, and then the model with the greater this area value can usually provide better diagnostic capability there, all right, or predictive ability. So I kind of increase this slide and just in the last minute, so apologize, didn't include in the handout, but this is the idea we have here. So we made lots of assumptions. Back to the assumptions again, okay, we need independent assumptions and a linear relationship between log out and the continuous cohorts. Okay, this is the assumption we need to make when you use the continuous cohorts. Okay, but if it's not continuous cohorts, like gender, like the smoking, that's okay. Basically, this assumption you do not need. And then constant outreach also need to be made across the values of all the continuous predictors. But we talked before, this assumption is not so constrained. The reason is we can, if it's not the case, we can categorize them. Or even you don't know if you should do it or not, you can categorize them first and estimate all the odds ratios to see if the linear trend is there or constant odds ratio is there. Okay, if it's there, you do not need to break them. Otherwise, you can break them. So I think the overall the assumption is not as strict as the linear regression model. How do I know the model is good or not? Okay, so statistically, there's a goodness fit test to see, okay, evaluate the overall if the model is a good fit or not. So scatter plot is still helpful, okay, just like we did before for the age. Okay, you can do those kind of scatter plot, just break into each, for each variable, break into groups and see the proportion of get that disease, what's their pattern, is that follows kind of a logical regression function format or not. All right, so that helps. And then there's a formal statistical test, is goodness fit test, can allow you to see, to evaluate if the model is appropriate or not, just like the R-square in the linear regression model. Okay, so if you statistically you find, okay, there's not significance, and then your conclusion is the model is adequate to fit the data. Otherwise, you can we can reject the hypothesis and say the model is not good enough, right? There's also some outliers may exist, just like all the model case. So if there's outliers, you need to probably identify the observations that may have a big impact on the model fit. Okay, and just like the linear regression, we need to look at the residuals, do some residual analysis, and even though in this case in the logical regression model the residual analysis is a little bit difficult. Okay, but we have a software package to support that one. Still can get the residual estimates to evaluate give you the test statistic to evaluate some observations that may be outliers. You need to double check and to see if there are outliers or some true cases. So there are some diagnostic index to assess how the coefficient estimate changes if a subject was deleted. That's basically the idea you can do, and to allow you to evaluate basically for each observation. I can give you an evaluation of if this observation is a significantly important or not, or has a big impact on my model fitting or not. All right. So to summarize this one, the logistic regression model allows us to deal with the case with the outcome variables being a binary variable. That's most often the case. And it allows you to assess multiple predictor variables. And these predictor variables can be continuous, nominals, or ordinal categorical variables. It can provide adjust estimates of the odds ratios. All right. And it can test for association of risk factors and assess their possible interactions for you, all right? And it can be used as a predictive model, okay, and then to classify the future patients, and then do some classification there. All right, so there are some references here. I think these textbooks are helpful to learn more details about the logical regression model, and some resources for the the division of biostatistics provide consulting service, so you can get help there. And we have drop-in sessions also. So if you have practical projects there, and you can get help there also. So I think my stop just ends here. Any questions? Thank you for your attention.